90 million miles from us lies the greatest power in the solar system. It lights our lives and warms our world, the sun. For most of us, our sun remains a mystery, too bright to look at with the naked eye. But we're going to show you our star as you've never seen it before.
Oh my goodness.
We'll discover what the latest science is revealing about our very own star. From the extraordinary drama of a total eclipse to the magical beauty of the northern lights. We'll be exploring the sun's most spectacular displays and what they can tell us about its inner workings. We'll investigate the sun's changing nature, its dramatic cycles of activity.
Is it coming our way or not? And if so, how fast?
And the unexpected effects these cycles can have on our lives. The sun is more active now than it has been for a decade, and a new generation of satellites is capturing it in more detail than ever before. Come explore how new science is revealing the secret history of the sun. To begin to understand the sun's extraordinary power and its changing cycles of activity, we need the help of one of the most dramatic events in the astronomical calendar, a total solar eclipse. November 2012, Cairns, Australia. In 48 hours, there's going to be a total eclipse, and people have come from across the globe to catch it. But this one's special because it promises to reveal something crucial about what's going on with our sun. To get an eclipse, the moon must drift between the sun and the Earth. At what's called first contact, the moon begins to block it. But what's extraordinary is what happens when the sun is completely covered. That moment of totality reveals something that's normally hidden by the sun's glare, the sun's faint atmosphere, the corona. And it's the corona that's key to what this eclipse can tell us. We're very lucky. The Earth is the only planet in the solar system from where you can witness a total eclipse. Because although the moon is 400 times smaller than the sun, it's also 400 times closer. So at a total eclipse, it appears to be exactly the same size. There's a total eclipse on average every 18 months, so they're not exactly rare. But catching one isn't easy. The narrow shadow paths they trace on the Earth's surface are far more likely to pass over uninhabited regions, such as the oceans, than a populated area like Cairns. And the timing of this eclipse is significant. Right now, we're due to be at solar maximum, the period of greatest activity in the sun cycle. But each maximum is slightly different, so scientists need to confirm that we've actually reached it.
Just click on that.
Delivery.
One way to confirm solar maximum is to study the sun's corona during totality. It's what makes this eclipse especially exciting, even to the most hardened eclipse chasers. Astronomer Francisco Diego has seen 17 total eclipses. This time, he's advising a group of 100 British enthusiasts, but he's also brought his own equipment. A camera and some filters are all Francisco needs to take photographs of the corona. It's the shape of the corona in the photos that will show him if we're at solar maximum.
The shape of the solar corona is modulated by magnetic fields on the sun, which in turn are the consequence of an 11-year cycle. So this 11-year cycle of activity in the sun goes from very high activity, low activity, and then high again. And in that process, the shape of the solar corona is changing all the time. For example, when the corona is very round, that means the solar activity is at the maximum. You have a lot of myths and legends about the disappearance of the sun in the middle of the day, and still today, I think we have that fear. When we see that shadow coming, it comes at twice the speed of sound, very, very fast, and covers the whole landscape in a matter of a couple of minutes, and it is terrifying, and we still feel that. I mean, you're operating your equipment, and you still feel that fear and that anxiety of the sun disappearing in the middle of the day. So, in a way, yes, it will be one of the reasons that we travel to those remote places to witness and to feel this very, very deep emotion, this link that we have with nature, with natural phenomena.
Francisco will only have 2 minutes in which to get a successful picture of the corona. 5 a.m., the day of the eclipse. The sun is already rising. First contact is only 10 minutes away.
Oh, yeah. We're well on our way.
The moon has begun to cover the sun. But the sun is so bright that there is no noticeable darkening of the daylight until much closer to totality.
From now on, there is something strange in the light. You see, the colors are fading.
What do you think, Francisco? It's looking quite skinny now.
It's quite skinny. It's about 10 minutes before totality. Yeah. So this is where things are going to happen faster and faster. The darkness is going to really come much quicker.
Oh my goodness. Most amazing thing. I can't believe how beautiful it is.
The moon has completely blocked the disk of the sun. A delicate halo is all that remains. It's the corona. Francisco now has 2 minutes and 2 seconds to get the photos he needs.
Here it comes.
Isn't that amazing? Amazing. Yeah, that's great. The whole thing is over, and you are left with this image, as I have right now in my mind, the image of the solar corona there in that bit of the landscape. It's very, very intense, very fast, and you want to relax and to feel that what you just saw.
But what do Francisco's photos show? Has the sun reached its peak of activity? Astronomer Francisco Diego is trying to determine what stage the sun is in its 11-year cycle. This is Francisco's photograph of the corona at a past solar minimum. The corona has a vertical axis. It is ordered and calm. But this is his 2012 Australian eclipse photo. The corona goes out in all directions. It's the sun at its most active, solar maximum. So why does the sun go through these cycles of activity? To understand why there is a solar cycle at all, we need to know what's going on deep within the sun. It's a place we can never go to. But we can learn a lot from something that makes the journey all the way from the core of the sun to us, here on Earth. Sunlight. We think of sunlight as simply coming from the sun's surface. But its journey is far more epic. It starts deep inside the sun, a vast burning mass of hydrogen and helium. It's the sun's enormous mass that creates the conditions to produce sunlight. Its intense gravitational pull forces the sun into layers, each with its own special properties. Beneath the thin outer peel is a 125,000-mile thick layer where hot material rises and falls. The next layer radiates the sun's heat outwards. And at around 250,000 miles is the core, a 16 million degree furnace where the entire mass of the sun pushes inwards. The pressure is so vast that the very atoms are fused together. And it's that fusion reaction between atoms of hydrogen that gives birth to the sun's heat and light. The scientists here at the National Ignition Facility in California are trying to make a tiny sun and thus recreate fusion. Fusion in the sun's core keeps itself going, powered only by the sun's mass. Copying that here on Earth is not easy.
All of this is about getting ignition that could change the world.
Here in this dust-free environment, Beth Zanitas creates hydrogen fuel capsules smaller than a grain of rice and destined for a very violent fate.
This is called a capsule filled tube assembly. It's a 2-millimeter diameter plastic capsule. 192 laser beams converge on the capsule, and that plastic material blows away from the capsule when it gets hot and under high pressure. And that causes a subsequent reaction of the fuel air to be compressed so that the hydrogen atoms fuse.
To get those atoms to fuse, they need to generate similar pressures to the sun's core. 340 billion times the pressure on Earth. It's not easy, but there is a way. The 192 individual laser beams they use are each more powerful than any other laser on the planet. And they all fire at a spherical chamber at the heart of the complex. This is the target chamber. And when the lasers hit the fuel capsule at its center, they bring the atoms together with the same force as in the sun's core. But to truly mimic our star, the NIF team needs to pull off an even greater trick.
Proceeding to system shot countdown state.
Once ignited, that fusion reaction must keep itself going.
Starting system shot sequence on my mark. 3, 2, 1, mark.
May I have your attention? Preparations for shot operations in Laser Bay 2 are underway. Leave Laser Bay 2 now.
It's not without its dangers. Before every shot, the area is evacuated. 3-foot-thick steel and concrete doors enclose the target chamber. A misfire from the most powerful laser in the world could cause a catastrophic explosion.
MOR ready for system shot countdown clock.
And even the smallest fusion reaction unleashes a lethal blast of neutrons and high-energy light.
3, 2, 1.
The only visible sign is this flash from the world's biggest laser as it fires. But inside that fuel capsule, they're hoping to create their tiny sun, and with it, man-made sunlight. Another day, another shot at creating nuclear fusion. The NIF team routinely achieve momentary fusion, but this time, no self-sustaining fusion. Yet if we could achieve it on Earth, we'd have the sun's energy at our fingertips.
Recreating a small sun in this target chamber that's not too far away is always daunting in a lot of respects. We will get there eventually.
It's that elusive trick of generating endless energy that makes our sun so miraculous. The result is the birth of sunlight in the sun's core in particles of light energy known as photons. But their journey is far from over. Imagine this pinball is a photon newly created in the sun's core. That light must now reach the sun's surface. But it's a very difficult journey, because in between the core of the sun and the surface, there is a seething mass of superheated gas called plasma. The particles of plasma are so hot, they hurtle at high speed in every direction. So like the pinball, the photon can't take a direct route out. It's forever colliding with obstacles, moving at thousands of miles an hour. With hundreds of thousands of miles of plasma to cross between the sun's core and its surface, even though it's traveling at the speed of light, a photon of sunlight will take between 10,000 and 1,000,000 years just to get from the core of the sun to the surface. And then, freedom. What we think of as sunlight's journey, the 90 million miles from the sun to the Earth, is only the last 8 minutes of an odyssey that could have taken thousands and thousands of years. But this extraordinary journey raises a question. Fusion in the core never stops. So why does the sun's activity go up and down with the 11-year solar cycle? To understand, we need to know what's happening between the core and the surface. As the sun's plasma gets heated from below, it rises up to the surface of the sun, like steam rising in a kettle. The plasma is so hot, it is also electrically charged. And because it moves up and down with the convection currents, this creates huge magnetic fields. And that's not all. The sun, like the Earth, spins on an axis, so plasma also flows sideways. And as the sun builds up to solar maximum, the magnetic fields get wound up and tangled. At times of high solar activity, those magnetic loops break out from the surface of the sun, drawing the sun's plasma with them. This one loop is many times bigger than the Earth. But solar maximum has another implication. It's when the sun sends pulses of solar wind towards the Earth. The solar wind is a constant stream of particles flowing out from the sun, bombarding the Earth's own magnetic field. We can't see it directly, but we can see its effects. The aurora, the legendary northern and southern lights. This is time-lapse photography of the aurora seen from the International Space Station. But to see this evidence of the solar wind with your own eyes, you need to head not to the most sun-drenched parts of the world, but to some of the coolest, and at a time of year when they receive the least sunlight. This is Lapland in Arctic Sweden. It's February, negative 19 degrees, and a moonless winter night is about to fall. These are perfect aurora conditions. As the solar wind encounters the Earth's magnetic field, it sends energy down our magnetic field lines toward the poles, causing our atmosphere to luminesce in ghostly colors. That's what creates the aurora. Now is a good time to see it, because the solar maximum is when the solar wind gusts most strongly. Patricia Cowan knows better than anyone what it takes to capture the aurora. She was so bewitched by it, she moved from England to live in Lapland. Patricia's photographed the aurora thousands of times in the 16 years she's lived here.
The very first time I saw the aurora was a really nerve-tingling experience, because I had read and sort of explored a little bit about the aurora, but had no conception of the hugeness, the size, the sense of energy that the aurora gives. And when you are out alone under this totally mind-blowing experience, it just makes you feel very, very small. And even though that was 15, 16 years ago, I can still remember how I felt and what I saw that night. I don't think that will ever, ever leave me. Never.
It may be cold here in Lapland, but this is a hot spot for seeing the aurora. The people who live here know that it's not the twilight days of winter, but it's dark nights when the sun makes its most spectacular appearance. Thousands of people come here from across the globe to see the northern lights. But it's not just tourists and photographers who are drawn here. It's a perfect backdrop for scientists interested in an important question. How well is our magnetic field holding up to the constant battering of the solar wind? The aurora is but a faint trace of the solar wind's true strength. Out there is a violent collision where it meets the Earth's magnetic field. That thin shell gives us vital shelter. It's the last night in Sweden for our camera crew. It's tonight or never.
Oh my goodness, look at those stars. It's so clear. Oh my goodness, look at that! Look what's happening in the sky!
With ordinary cameras, you can see it faintly, but to capture it in its full glory, you need time-lapse cameras.
It just gives me an absolute physical vibe and thrill. I cannot imagine ever living anywhere that I can't experience the Northern Lights during the rest of my lifetime. It means that much to me.
The aurora is a stunningly beautiful display of the solar wind, but it's also a reminder that thanks to our magnetic field, the majority never reaches us. It's a mere hint of the vast amount of radiation and particles that the sun sends our way. During periods of high solar activity, the magnetic loops in the sun's atmosphere become tangled and knotted, and occasionally they snap. 1 billion tons of mass from the sun being ejected into space. Such eruptions are called coronal mass ejections. These solar storms are the most high-energy events in the solar system, and the sun unleashes more of them at solar maximum than at any other time. The clouds of plasma they send our way travel at alarming speeds. To cover the 90 million miles from the sun, seen here reduced in scale on the right, to the Earth on the left, can take less than a day. Solar storms can destroy satellites, silence communications, and ground aircraft. But the link in our modern lives that threatens most is our dependence on electricity. The highly charged particles of coronal mass ejections can induce powerful electrical currents on the Earth's surface, overloading circuits and melting transformers. This could take out lighting, heating, our ability to refrigerate and cook food, operate fuel pumps, sanitation, and water supplies. We know we're vulnerable because we've been hit in the past. In Quebec, the entire power grid went down after a solar storm in 1989, plunging millions into freezing darkness. But we're not helpless. Technology and systems are already being built that are resilient to solar storms, and the best thing of all would be to have an early warning system. Fortunately, there is one inside this building. The Space Weather Prediction Center in Colorado is the only team on the planet solely dedicated to watching for solar storms. The aim is to give even a few hours warning for governments, the power grid, aviation, and space industries to get ready when a storm's on its way. The forecasters have their eyes peeled for the telltale signs that a storm could be coming.
Space weather really starts with sunspots. So if we don't have big, complex sunspots, we really don't have those source regions for the big, significant activity. So essentially, before we get a big event, before we get that first clue that we should start looking for the other pieces, we're really looking at the sunspots. How big are they? How much are they changing? The black and white here is if you could see magnetically, how magnetically complex they are. So essentially, the two ends of a magnet, so to speak, the white and the black, if those get very close together, you can get very, very explosive reconnections. The next piece we start looking for on chronograph images, for example, where we've essentially blocked out the sun and watched the outer atmosphere around that. You start to watch and see, with this eruption, was there a big portion of the outer atmosphere blown into space? And if so, is it headed right at us?
Every one of these amazing images is being beamed to us from the new generation of solar satellites. They are our eyes in space to keep watch over the sun. They can see the sun with visible light, magnetic fields, X-rays, ultraviolet. On a typical day near solar maximum, the sun will send out 3 coronal mass ejections. Fortunately, today, there haven't been any. But dramatic events can happen with little warning. Dramatic solar weather can happen any day, any time.
I picked out from late October 2003 of probably the last significant, really big round of space weather activity that we had. We've blocked out the sun so we can see the atmosphere. You'll see the eruption. It looks like a halo coming straight at you. It was going at tremendous speed, so it made it here in just under a day. So we have the levels 1 through 5, just like a hurricane or tornado, and it was pegged at that 5-level storm.
That solar storm took out the power grid in the Swedish city of Malmö. Tens of thousands were left without electricity. On that occasion, the Earth was only struck a glancing blow, but we can't be sure that next time we'll be so lucky.
Today, if we saw this happen again, we'd be able to give our partners in the key industries, like the electric power industry, a heads up to say, hey, prepare your systems, keep them as safe as you can.
Day and night, solar weather is always happening. We can't afford to ignore it. But we're only just beginning to understand it. And crucially, the sun's activity is highly dependent on which stage of its cycle it's at. But the latest research suggests that the cycles themselves could be changing. We could be living through bigger shifts in the sun's behavior than we thought. And the evidence comes from a feature of the sun that's been plain to see even before the invention of the telescope. Early astronomers like Galileo risked damaging their eyes to look at the sun on cloudy days or at sunset and sunrise. And they spotted dark features on the surface of the sun that we now know as sunspots. Thanks to those early astronomers, sunspots are one of the few clues we have of the sun's long-term behavior. The key is what causes them. It's been known for centuries that sunspots are cooler. While most of the sun's surface is at 10,000 degrees Fahrenheit, sunspots are at around 6,000. That's the same temperature as the spark from an arc welder. Cool in comparison to the rest of the sun. But sunspots are still ferociously hot, active areas. And new research is revealing something surprising about them. As the sun approaches solar maximum and the magnetic field lines beneath its surface become tangled, the flow of plasma within is disrupted. Hot material from the interior can't rise to the surface. The result is zones of cooler plasma, sunspots. They are like windows in the sun's surface, through which we can study what's happening inside the sun itself. The McMath Solar Telescope in Arizona is the largest in the world. 17 years ago, a study of sunspots began here, led by a group of astronomers, including Matt Penn. Matt and his colleagues began to look at the strength of the magnetic fields within sunspots.
Well, sunspots have revealed a lot about the interior of the sun. It's the surface manifestation of the magnetic field. We know the sun is filled with magnetic fields on the interior and also in the atmosphere, but sunspots are the surface detail of that. The questions about what generates the magnetic field and how it changes with time can be addressed by looking at the clues that sunspots give us on the surface. So when we started making these measurements, we weren't sure exactly what we would find. One idea was that as the sunspot number increased to a maximum and then decreased to a minimum, we might see that the magnetic field would change as well. It might increase to a maximum during the maximum of a sunspot cycle and then decrease to a minimum at the minimum. Turns out that when we looked at the data, that's not exactly what we saw.
Matt has found an ingenious way of measuring the strength of the sunspot's magnetic fields. Scientist Matt Penn is using a clever new technique to measure the strength of sunspots' magnetic fields, a change in the infrared light coming from them.
So what we're doing is measuring the magnetic field with a spectral line, and we've done a survey of about 3,000 sunspots over the past 10 years, measuring the magnetic field strength in each sunspot.
And what he discovered is surprising. Instead of rising and falling in line with the solar cycle as expected, the magnetic strength of sunspots has been steadily decreasing year by year.
As a function of time, the magnetic field in sunspots is getting weaker and weaker. Now, this is important because when we look at sunspots, we don't see any sunspots with magnetic fields below a threshold, a 1500 Gauss threshold. So as this decrease continues, if it does, into the future, we'll eventually get to the point where the magnetic fields erupting from the sun can't form dark spots. So a decreasing trend means that in the future, we may not have any sunspots at all.
It's an extraordinary result. The trend suggests that over and above the familiar 11-year solar cycle, there are bigger patterns in the sun's activity. And in the long term, we may be heading for an extended quiet period, what solar scientists call a grand minimum. Intriguingly, we've been here before. Thanks to those historical records, we know that around 350 years ago, sunspots almost vanished for 70 years.
So this is something new, but it suggests that we might be entering a period that we saw in history. In the mid-1600s, we entered a period called the Maunder minimum, where the number of sunspots in successive sunspot cycles decreased, and for a while, for 4 sunspot cycles, there were no sunspots on the sun. During that time, there's some evidence that the climate of the Earth actually changed. And so if we are entering another minimum period like the Maunder minimum, we'll be very interested to see if the climate of the Earth is going to change as well.
A grand minimum would be a double-edged sword. It might mean fewer solar storms, something in our favor. But it could also mean a dramatic change in our weather. The previous grand minimum coincided with a period of brutally harsh winters in Europe and North America. The River Thames in London froze solid. It was known as the Little Ice Age. Are we heading for another?
So in the long-term life of the sun, we'd love to know what's going on. It's a big unknown, a big mystery.
Our sun is 4.5 billion years old. We don't know how it was behaving a billion years ago, and we don't know what it will do a billion years from now. We're witnessing just a tiny sliver of the lifetime of the sun. Even several hundred years of data cannot tell us if this long-term change is part of a much bigger cycle in the sun's behavior that we've only just begun to glimpse. But what's emerging is that even the pattern we thought we knew, the 11-year solar cycle, isn't the full story. The new research is hinting that there are greater, longer-term patterns in the sun, and they could have profound influences on our planet and on us. In this bright age of solar research, we're getting closer than ever before to understanding the hidden mysteries inside our star, the sun.